So far this semester, when we've talked about pointers in C, it's been entirely in the context of arrays. We know that we can have pointer variables and assign them to point to the beginning of an array. And we know that when we pass an array into a function, what's really being passed is a pointer. And we also know that we can use indexing to access the elements of an array using a pointer variable. But in fact, there's quite a bit more that we can do with pointers. For one thing, we can make a pointer variable point to anything we want, not just an array. Here I've declared one variable of type float and another variable of type pointer to float. And I can make that pointer to float point to our float variable by assigning into the pointer variable the address of our float. So ampersand in C is the address of operator, and it evaluates to the location in memory where a particular variable is stored. So, having made this assignment, we can then use our float pointer variable to access the data in the float. In C, the star operator is known as the dereference operator, and it means follow the pointer and get the value that it's pointing to. So here, we are printing a floating point value, and we are getting that by following our float pointer. And since the float pointer stores the address of our float, this will retrieve the value 0.5 from the memory location that our float pointer is pointing to. We can show more directly what the ampersand operator is doing by printing out the address that it's giving us. In a printf statement, %p for pointer is how we print an address, and we can get the address of our float variable f to give to that printf statement. It helps if I save. And now we get a hexadecimal value, which is the address in the stack frame for main where the variable f is being stored. If we were to duplicate this line and print out fp without the dereference operator, so rather than following the pointer, we are just printing out the value of the pointer, which we know is a memory address, we should get the same address that we got for our variable f. Still helps if I save. And we get the same hex address for the address of f and the value stored in the pointer variable when we run the program. But of note, on different runs of the program, we are getting different addresses because the stack gets placed at a slightly different location in memory on different runs of our program. If we add 2 to the value of the pointer, then we are performing pointer arithmetic. Let's save, compile, and run to see what this does. So the address of f ended with EC, and if we added 2 to the hexadecimal value EC, we should have gotten EE. But instead, we got F4, which is 8 larger than EC. Hopefully, after seeing lots of stack addresses that advance by 4, you have a guess as to what's going on here, which is that a float variable in C takes up 4 bytes of memory. And so, when we add 2 to a float pointer, the pointer arithmetic evaluates to the address stored in the pointer plus 2 of the size it takes to store that type of data. So since floats take up 4 bytes and fp is a pointer to float, we will advance by 2 floats in memory when we add 2 to the pointer, and so we've advanced by 8 addresses. We can verify that it takes 4 bytes to store a float with the sizeof operator. The sizeof operator returns a long, so I need to change the type of thing I am printing. And it would help if I put a new line. And we see that the size of a float is 4. It's a common mistake in C to think that sizeof can be used to tell us the size of an array, but in fact, rather than telling us the number of elements, it tells us the amount of memory. And if what we have instead is a pointer, because, for example, we called a function and passed the array, what we get is the amount of memory that it takes to store an int pointer, which is 8 bytes, or 64 bits, because we are working on a 64-bit operating system. So the sizeof operator is not used for determining the size of an array. In C, it is up to you as the programmer to keep track of the size of your array and pass that around as needed, whereas sizeof is useful for telling us how much memory it takes to store a particular type of data. And that is useful when we are allocating memory dynamically. All of the arrays we have seen so far have been declared like this, with a constant giving the number of elements in the array. But if you don't know at the time you are writing the program how many elements the array is going to have, if, for example, you're going to read a bunch of data from a file, or from a web page, or from user input, then having a constant-sized array is not necessarily a good solution. So what we can do instead is use dynamic memory allocation, where we call the function Malloc. The Malloc function stands for memory allocate, and it allocates a chunk of memory and returns a pointer to the memory that has been allocated. This function lives in the standard library, so we'll need to include that. And Malloc takes as input the number of bytes of memory that we want to allocate. So if we wanted to allocate space to store an array of 100 floating point values, we could pass to Malloc 100 times the size of a float. And since size of float tells us how many bytes of memory are needed to store one float, then we can calculate the amount of memory required for 100 floats and ask for that many bytes when we call Malloc. Malloc then returns the address of the memory that it allocated, so we can store that address in a pointer variable. So there are several reasons why this approach to dynamic memory allocation is more useful than statically allocating arrays. One is that we don't need to know in advance how much memory we're going to be using. This can be a calculation that we do on the fly based on other inputs that our program has received. Additionally, if we are building data structures, like a linked list, or a binary search tree, or your favorite data structure from 221, then those data structures typically need the ability to add new elements and new nodes to store those elements dynamically. And finally, dynamic memory allocation makes it much easier to pass data back and forth between different functions. In both of these cases, we have allocated a big chunk of memory, but we have no idea what's being stored in the array right now. So it would make sense to initialize these arrays in a loop. And really, what would be great is if we could write a function that allocates an array and initializes all of the elements to 0, and then gives us back the array once it has been fully initialized. And so we could write a function called zeros that initializes an array full of zeros of a length that we specify as input. The trouble here is that if we create the array in our function zeros, then this array lives in the stack frame for the zeros function. And so when the zeros function returns, that stack frame collapses back down, and now, if we were to call some other function, that memory would get overwritten with the stack frame for the new function. So we can show that this doesn't actually work. The compiler is warning us that we are returning the address of a local variable, and that's a bad idea. And we see that it's a bad idea when we run the program. And at best, this second call to zeros would have overwritten the first one, and so our result would have been wrong. But actually, we got a segmentation fault because we tried to access memory that was out of bounds. The zeroth element of the array was far enough past the memory that our program was currently using that when we tried to access that memory location, the operating system told us no, and our program crashed. So we could fix this by having our variable array be dynamically allocated. So now we are using Malloc to allocate memory, and we are allocating length times the size of a float. So we are allocating space for the required number of floats. And now, if we compile and run, we have that A and B are pointing to different dynamically allocated chunks of memory. And so the zeroth element of A was unaffected by our creation of an additional array. And we could print out the zeroth element of B and verify that it was initialized correctly to 0. So whenever we call malloc, we are allocating a chunk of memory. And that chunk of memory is located in the heap segment. If we were to print out the address where the variable A is stored and the address where the variable A is pointing, it helps if I call the right function. We get addresses that are at totally different ends of our program's address space. Note that these are 12-digit hex values, and so they are 48-bit numbers, and so the difference between these two values is in the trillions. And that's because the stack segment starts at the bottom of our program's address space and grows upward, and the heap segment, which is where dynamic memory is located, starts near the top of our program's address space and grows downward. And one difference between the stack and the heap is that memory on the heap is not automatically cleaned up the way memory on the stack is. As we've seen in assembly, when we return from a function call, the stack frame for that function gets cleaned up. We move the stack pointer and base pointer back down, meaning that we are no longer using the memory that was holding the local variables for that function. Memory on the heap, however, does not get cleaned up automatically. We have to explicitly free heap memory when we are done with it. And so, before the end of our program, we should call the function free on each of the chunks of memory that we created with malloc. So A is a pointer to one of the things that we allocated with malloc, and B is also a pointer to another chunk of memory that we allocated with malloc. So if we call free on A and B, then we have deallocated both of the chunks of memory that we created. This causes no visible difference in the functioning of our program, but we can detect the difference by running Valgrind on our program. When I run Valgrind on the version of the program where I have not called free, it tells me that there was a memory leak where we definitely lost 800 bytes of data in 2 blocks. That's because we had 2 blocks that were each 400 bytes of data that we allocated with Malloc and never freed. If we put the free statements back, recompile, and run Valgrind again, now it tells us that all heap blocks were freed, no memory leaks are possible. A memory leak is when a program allocates memory on the heap and never frees it. In actuality, it's not a big problem to run the version of my program that doesn't call free. The operating system is able to clean up the memory that my program was using when the program exits. But memory leaks, where memory is dynamically allocated and never freed, are a big problem in practice. When a program is running for a long time, memory leaks can build up and use up system resources to the point where the program crashes or the program gets in the way of the computer doing anything else. So in this class, to get you used to the idea of freeing any dynamic memory that you have allocated when you are done with it, we're going to enforce the guideline that on your C programs from now on, when you are allocating dynamic memory, you need to run Valgrind and confirm that your program has no memory leaks. If Valgrind says that your program has any memory leaks, then you need to go figure out where in your program you have allocated memory that isn't getting freed. Valgrind can also be very useful for identifying other sorts of memory errors. For example, if you went out of bounds on an array, remember that C doesn't check that for you. For example, here I'm accessing the 101st element of a 100-element array. And if I run Valgrind, it tells me that there was an invalid read of size 4, meaning I read data from memory at a memory location that was not correctly allocated, and it was of size 4 because we were reading 4 bytes of data since we accessed one float, and it takes 4 bytes to store a float. And it tells me that it happened in main, and it happened immediately following a block of size 400 that was allocated with Malloc. If I had compiled with -g, then it would also tell me where the memory was allocated. It was allocated on line 5, and where it was that we had this invalid access on line 22. So Valgrind can be an extremely useful tool for debugging, and so I encourage you to get into the habit of running Valgrind on your executable as part of your debugging process.